right, and my kiddos, you have your science spirals?
Yeah.
Science spirals, and you are gonna need a pencil. All right, check your whole body listening. And let's go over our learning target today. It's kind of general. I did that by design because thought we could have some fun with science. So really, I'm hoping by the end of this hour, I'm gonna cram a lot in. So we're gonna get it all in 1 hour. But I want you to be able to answer these questions and hopefully understand the vocabulary for a science unit that we're going to touch on throughout the year, and it's called Forces and Interactions. And at first I thought, oh gosh, I don't know how exciting that unit is. And then last night, my son is in physics. Oh, there's Charlie, yay. And we had so much fun coming up with ideas of things we could do with you guys to make this unit really, it's very interesting. And I realized I don't know everything about forces and interaction. And he taught me a lot. And I asked him if he could come be a guest speaker, but he's in classes, so he couldn't come. But I think if you are interested in physics, Cooper, can I see whole body listening? Thanks, buddy. That you will really enjoy this. And you might not even know this is an interest of yours, but maybe after today, it will be. If you've ever thought of being a skateboard park creator, designer, or maybe you do that at home, this might be your thing. Gabe is not in here right now, but Gabe this morning got up just to work on bike jumps. And so if you, and I know my class is really, I don't know how, daredevils is kind of what I'd call some of my students. So you might enjoy this science more than you'd realize. So it might sound simple, but it's exciting. What is motion? I bet you're already thinking, oh, I know that, Mrs. Aubin. What forces make things move? And then I love this one. What is friction? So this is what we're going to hopefully get through today and learn about. Some of the vocabulary we'll be hearing, and then hopefully you'll be adding to your vocabulary is the words weight, force, gravity, mass, motion, and friction. Okay, so I'm excited. I hope you guys are. So let me get to my screen. You guys ever heard of Discovery Education? Yeah. My favorite. So fun. They have a lot of good resources. So be thinking, I'm going to ask you right away. Here's my first question for you. What is motion? Get it formulated in your head. If you want to write it down in your science spiral, then you could write it down. You could draw a picture. I see you're demonstrating it for me, Mr. Bowers. I love it. What is motion? That's your first question, your first thought-provoking question. What is motion? You want to write down some words that you think describe motion. All right, what is motion? Mr. Bowers, do you want to unmute and share your thoughts on what motion is?
Something that moves, like when you're gooing and dancing.
Okay, so something, it's movement. Anybody want to add on to that? Yes, Haley.
When you're walking or like you're running, like your whole body like moves.
Running, walking are examples of movement. What else, Miss Sunny?
Like rolling.
Rolling could be an example of movement. What is motion? Are we saying is movement? What are you thinking? August. Riding a bike shows motion. And I think I want to say movement as a synonym. Anybody else have ideas at home? What is motion? That was my question. Okay, I'm going to let other people have a turn. Logan?
It's how you're feeling.
Can you say it again one more time?
How you're feeling.
how you're feeling?
Actually, how you're feeling?
Feeling, right?
Emotion.
Oh, I think you're thinking, right, Finn. I think you misunderstood, Logan, and you're thinking of emotions. And that is right. Emotions are your feelings. We're looking at the word motion, M-O-T-I-O-N. Charlie Van Rickley, can you unmute and share?
Ocean tides. Something that goes back and forth.
Ocean tides, yes, which is controlled by the forces we're going to talk about today, and the moon and the earth and the tides coming in and out is part of motion. One more.
Swimming.
Swimming, you are moving when you're swimming? Okay, let's watch this quick video. I've got a lot of little videos we're going to watch and see if this helps explain our topic a little bit.
Think about some of the ways things moved around you today. You moved food into your mouth as you ate breakfast. Your body moved as you walked out of your home. Cars, trucks, buses, and people moved around you as you traveled to school. And maybe you even moved a frisbee when you threw it to a friend. Moving things are all around us. You observe. What caused this rocking chair to move?
What do you think? What caused the rocking chair to move?
Somebody pushed it.
What do you think?
Motion.
Someone pushed it.
Somebody had to push it. It's a force, right? We call that force pushing. There are other forces besides that, but that's one of our forces, which is going to be the next thing that we're going to be talking about. So if pushing it caused the rocking chair to move, I want you to think about, here, let's look down. I've got another picture here. Think about objects you've seen move. Like think about a ball, especially like a bowling ball. What do you do to get the bowling ball to hit the pins, Josh? What do you do?
You force the ball.
Okay, you give it force to make it roll, right? You're kind of pushing it down the lane. What else are you thinking?
Like these little things for kids. It's like a little ramp. You put the bowling ball in there.
Oh, that's awesome that you brought that up. That ramp, and we'll be doing a little experiment later thinking about angles and how that helps with our motion. Did you have something to add?
Yeah, the person walks and rolls it to knock down the pin.
Very good. So he said, August said the person walks and then rolls it down to knock down the pins. So how does it stop? How does the bowling ball stop? Elena?
It goes down and then it gets knocked down.
But how? How does it stop? Yeah, Evie.
The bowling pin slow it down and then it will like fall down and then it will hit the ground. It will stop.
Okay, so she said that the bowling pins actually slow it down and then it will hit the bottom and drop and then it's done. So does a moving object only stop moving if it hits another larger object like a wall?
No.
If you think that's the only way a moving object stops, give me a thumbs up. If you think there's another way an object can move, Robert, can I see your thumb? Put it down. If you think there's another way it can move. Isabella, can you unmute and explain your thinking?
The way things can be forced to move is like when magnets hit a same connection, they magnetize, and when you put the opposite force, they don't connect and they bend.
Very interesting. How else can an object stop that's in motion besides hitting something else? Yeah, Ryder.
If it rolls for too long, when it's something flat, the air kind of starts to stop it because it doesn't get as much force.
Okay, so he is saying that, so can we use an example of like a soccer ball?
Yeah.
So say you kick a soccer ball on a field, and he says that eventually it doesn't have to hit anything, it'll stop. Does it just run out of force? No, what you said something good. You said something about air. There might be some air pressure, but what else might stop a ball? What makes things stop besides just hitting a wall? What are you thinking, Charlie? Okay, so something else like water. What else were you thinking?
When they go up the ramp, it'll start slowing it down.
Oh, like when your brakes go out and you need to go up that truck ramp. A ramp could make you slow down or stop. What else? Sure. Okay, so August said if you rolled a bowling ball or any kind of ball into sand or quicksand, he said it would sink, but even sand, it wouldn't keep going, right? Okay, so we're going to talk more about that as we go. You guys have a lot more schema than I realized. Good for you. So now we're going to talk about what forces make things move. So we know motion is movement, yes? We're going to skip this. We know motion's movement, and we know that to cause that movement, we need to cause it. What are the forces? So there are a few things that make things move. Before I share this with you, I want to know, how do I get there? I want to know, what do you already know? What forces are there? We came up with one force, and I want to share my screen. In your notebook, on a piece of paper, I want you to make a double T chart. Have you ever heard of one of those?
Yeah.
You make two lines and then a T across. And let's talk about some forces we know. There's plenty, but we're going to just focus on, I heard one of them, one of you guys said that you had to make that rocking chair move, we had to push it, right? So we have a pushing force. Let's write pushing. And I think I can make this darker. Find my right marker so you guys can see it better. Here, let me use a darker color. So pushing, oh, I heard it. Who said it? Pulling is another force. Pushing, pulling. What other force? This one I don't know that you're gonna get. Who said it? I am so impressed. Miss Abby said gravity. So we have, did you hear a lot of gravities? Oh my gosh. I need to hear, don't they? I'm so happy since we're minimizing it. All right, so what are some examples of things that we use for pushing? What might we push? Let's do some brainstorming. Elena. A desk, yeah. I have to push desks all the time in the classroom. What else might we push?
A door.
You push a door? Yeah, Sunny.
A button.
You push on a button when you're trying to get it in the hole. Sure. How about some hands at home? Can anyone else think of things that we might push Paxton, you're a science guy. Can you think of something we could push? Think of being at a store.
He's pushing a chair right now. Or a swing. Oh, a swing.
Guys, let's be respectful. A chair? I think you're doing that right now, Paxton. All right, Jensen.
A wheelchair?
Oh, yes, wheelchair. Can't recognize you guys with your hats. Bird.
The cart is when you go shopping with friends.
Yes, a cart. Grocery cart or just a cart at any store. All right, that's great examples. What about pulling? What might you pull? Cole. A lever. You got to pull a lever down, like for a fire drill. Cooper. A wagon. Charlie. Pull a what? Button again, you might pull on it. Okay. Yes, August. We'll come back to you. How about Paxton again? I see your hand is up.
Tug of war?
Tug of war. Tug of war. So a rope, right? You might be, and that's an awesome example. We used to play that a lot as kids. I don't think they do it anymore. Do you guys ever play tug of war? Oh, with your dogs, yeah. Okay. Haley, let's hear from Miss Calendar.
A door. You can pull a door open.
Sure, I love it. Okay, now gravity. What? Oh, this is going to be, we could write forever. What things are pulled by gravity? Trying to see if I have hands at home. All right, Henrik. Satellite. What are you thinking, Sunny? Desk? August? Space. What do you mean by that?
Space.
So everything has like some kind of gravitational pull? Okay, so what in space? Do we want to say the
Asteroids. The moon.
There's a gravitational force in the, with the moon. What are you thinking, Elena? I can't hear you, honey. A book? Yeah, if you drop a book, if you hold it up and drop it, where's it going to go?
On the ground.
Go to the ground. What are you thinking? Bullet? Okay, what about even an apple if it falls off a tree? Would an apple fall to the ground? Could we keep going? We could go. So here are some of the forces that we think about and probably are around all day long. Right now I see people using a force to push chairs. I see some of you using forces to push on your pencil and press on your face. So forces are part of our everyday life. So let's look, we're going to learn a little bit more.
In this program, we are going to learn about force. What is force? Force is a push or a pull. Forces make things change their motion. When a person pulls on an oar, the boat moves forward. A push on a swing makes the swing go higher, and the person riding the swing go higher. Isaac Newton is a scientist who is responsible for explaining a lot of what we know about force and motion. Newton helped people understand that, like these dominoes, every time a force pushes or pulls an object, the motion of that object will push or pull something else.
Sometimes a force acts upon objects from a distance.
There you go with
The
your space.
gravitational pull of the
right?
sun on the Earth holds the Earth in orbit around the sun. Gravity is also the force that pulls us and everything around us back towards the Earth. To fight the Earth's gravitational pull and leave the Earth, we need a powerful push force that we get from rockets. Sometimes a force acts on an object by contact. For example, when a bat hits a baseball, the bat makes contact with the ball, and the ball changes its motion. There are different kinds of contact forces. Friction is a contact force. Friction is made when an object, like these tires, try to move across the surface of the road. When an object like this book is resting upon a surface, the surface is exerting an upward force. This is called a normal force. The force used to drive a nail into a piece of wood with a hammer is called an applied force. An applied force can be applied to an object by a person or another object. The world is full of motion, and all motion happens because of force.
Ellie, you ready? Okay.
Now that you better understand forces, think about this. Does gravity push or pull us towards the surface of the Earth?
Then we go which way?
No, I feel like just sitting, I think sitting up.
Okay. We're going to look at one more. So any kind of motion, I'll wait. Any kind of pushing or pulling on an object is called a force. Forces make objects move. I heard someone say this earlier, thinking about a swing. When something is, that you're pushing and pulling. When something is moving, it is in motion. So let's just watch this one real quick, and then we'll keep going with a little bit more about
In this
friction.
program, we are going to learn about motion. What is motion? Motion is the act of moving.
Thank you. Did we?
No.
I don't think so.
Motion is the act of moving. Everything moves. Fast or slow, motion happens
No,
all
sit down.
around us. There are things that never seem to stop
You guys
moving.
don't need to bring that in here. You'll get a time as soon as we're done.
And then
Because
some
then
that
everyone's
only
got to go
move
get
once in
theirs.
a great
We're
while.
not going to do it.
Motion is all about force. Force causes motion.
So this is what we
Force
talked
is
about,
either a
kicking, right?
push or a pull.
That was pushing and pulling.
When a force pushes an object forward, it could make the object move faster or move in a new direction. A force that
There's what we
pulls
talked
can
about,
make an
tug of
object
war.
move slower or make it stop completely. Gravity is a force that pulls objects towards the Earth.
So you were right, right?
I was gonna say.
Said it pulls us and doesn't push us.
Magnetism is another kind of
Isabella, that's what you were talking about.
Magnetism is the property found in magnets. Magnetism can pull or push objects. Isaac Newton was a scientist who observed motion and created 3 laws of motion. Newton's first law of motion tells us that every movement or change of movement is the result of a force. For example, the force force of a golf club causes the golf ball to roll. And when the ball stops rolling, it is a force that causes the ball to stop. Newton's second law of motion explains that the speed and direction of an object, like this baseball, is determined by the force, how hard the pitcher throws, and the mass of the ball. Newton's third law of motion explains that for every action, the batter hitting the ball, there is a reaction. The ball flies off at a different speed and direction. Like bowling balls, forces and motion set other forces and motion into action. Motion comes from motion. Every force comes from another force.
You need your science spirals and a pencil.
Now that you better understand motion, think about this. What determines the motion of a bowling ball?
Pushing.
Is that it though?
Force. Pushing force. Or the pushing force. Or whatever.
So what do you think? What determines the motion of a bowling ball?
Pushing and pushing.
Anybody at home want to answer that? Looking for hands, looking for hands. Nope. Okay, Elena, what do you think that determines the motion of a bowling ball? You don't need to sharpen that right now. Sit down. Thank you. The force of pushing it. Okay, what are you thinking, Serne? Say again? Same as her. Do you think anything else is going to affect that bowling ball and how it moves? Yes.
Gravity.
Gravity. What else might play a part in how fast your ball moves or how far it goes? What do you think, Ellie? Okay, we already said that. Anything different? I see two. How about Isabella?
When you are spinning magnets, they like spin
Okay,
like
we're
this.
talking about the bowling ball. Can you get with us on the bowling ball? What
No.
else? The air. What else? Max. How fast or slow you push it? Is there anything else that might affect it?
Your momentum.
Your momentum, which is what he's kind of talking about. Paxton. Paxton? Paxton?
Gravity.
Say it one more time.
Gravity.
Gravity. Okay, we said that. Lila, anything else?
There's the force of what it hits and how it hits it.
Very good. What about, like, what is it rolling on? If you put that ball in a field of grass versus the waxed slick wood that you roll it on, is it going to make a difference? Is it going to go as fast in grass as it is on a waxed slick piece of wood? Right? So what it is hitting, you're right. Thank you for sharing your thinking, Lila. That's very good. Okay, here's my question. Do forces always cause motion? Here's what I want you to do. Stand up if you think yes, that a force always causes motion. Anybody standing? Stand up if you think no, forces don't always cause motion. So Robert, I didn't see you stand up. Which one are you standing for, Leo? Which one are you standing for, Gavin? You got to stand for one of them, either yes or no. If you do not think that forces always cause motion, you're standing up right now. Okay, I see a lot of people standing. Robert, can you unmute and tell me why you think that just because you apply a force doesn't mean motion is going to happen? You guys can sit down. You guys are all right, but give an example.
Because motion is push and
But do forces always cause motion?
no.
How do you know?
Motion is one type of force.
No, we're talking about the forces we talked about are pushing, pulling, and gravity. But do they always cause motion? Do they always cause things to move? You say no. Give me an example. When do you use force and something doesn't move? Boys, I need your attention.
If I have a
So be thinking.
and I push it.
Write it down in your spiral. Write it down in your spiral. You got to talk a little louder, Robert. Give me an example of when you put force on something and there is no motion. That's what I want you to write in your spiral.
Isaac, just like
They got me. They worked hard. Oh, good. All right, anybody at home want to share an example? You all agree that just because there's a force doesn't mean there's a motion. So I need examples. What do you mean by that? Anybody willing to share? Write it down in your spiral what you're thinking, but I'd love to hear your ideas. Surene. Well, honey, you don't need to do that. What are we doing? I asked you to write down an example of when you use force and there's no motion. Yes, Ellie.
When you're trying to push something really heavy, but it won't
Abby?
because it's too heavy.
Okay, so Ellie's example is you might be trying to push something, like maybe you want to move a heavy rock out of your garden and it's too heavy. You can't get it to move and you're pushing, which is your force, but the rock is not moving. Any other examples? Yeah, Max. You might want to move a car out of the road that is stalled out, right? And you're not strong enough until you get enough people, right? Excellent example from Max. Yes. Marin says if you push on a wall, guess what? It's not going anywhere. Josh, you could push on the school and it's kind of like a cement brick wall. You're probably not going to make it go anywhere, right? All right. Good. You guys have so much schema. I'm so impressed. So if you think about that, that is called, but when forces are balanced, you're not going to have that motion. So think about who said it earlier when you guys gave the example of tug of war. That was so good. Paxton said that? So, and Cole. Hey guys, you don't need a pencil right now. Just sit down. You don't need a pencil. If you have the same force, right? The same amount of force, both teams, if you're playing tug of war, then there's not going to be any movement. It's called the forces being balanced.
In this program, we are going to learn about balanced force. What is balanced force? Balanced force is when the forces acting upon an object are equal and in the opposite direction.
See the video.
That's
Balanced
really weird.
force results in no motion. These books do not move.
Yes.
Because about it,
Whoa, that's so weird. Hold on, guys.
people are equally strong. For example, balance each other.
Yeah, randomly be weird.
Balanced forces keep objects in one place.
No, we haven't, honey. They use the same examples,
There
but
are
it's not
unbalanced
the same.
forces too.
Okay, so it's being weird.
If one football player exerts more force than another football player, The forces
Oh, that's
are
so
not
weird.
The liftoff of a space shuttle is an example of an unbalanced force in action.
So I'm trying to get it to
The
stop, but
thrust
it
of the
doesn't want
engine
to.
is greater than the weight of the rocket. You're going to learn about motion. What?
Oh, weird, you guys.
Balanced forces keep objects still and fixed in one place.
It won't let me get rid of it. So there we go. We're just going to get rid of that. All right.
Oh, it's because
Now that you better understand.
Oh, that's
balanced
because
forces,
that one came
think
on.
about this.
There it is.
Is this statue an example of a balanced force? Why or why not?
Oh, think about that. Look at that statue. It's not falling down.
Can you restart it? I don't even know what happened.
All right. So we talked about a little bit. I'll go back and see if it'll work.
We are going to learn about
Try again.
balanced force. What is balanced force?
You should be able to see it
Balanced
now.
force is when the forces acting upon an object are equal and in the opposite direction. Balanced force results in no motion. These books do not move because the pull of gravity on the books and the push of the table are equally strong. They balance each other. Balanced forces keep objects in one place. There are unbalanced forces too. If one football player exerts more force than another football player, the forces are not balanced. The liftoff of a space shuttle is an example of an unbalanced force in action.
Look at all
The
those
thrust of the
smoke
engine is
clouds.
greater than the weight of the rocket. Balanced forces keep objects
We have a
still.
lot of those here in Colorado, right, Sawyer? We have a lot of those.
Now that you better understand balanced forces, think about this. Is this statue an example of a balanced force? Why or why not?
Do you guys think yes or no? Give me a thumbs up or thumbs down. Thumb up or thumb down? Gavin, what do you think and why?
I think it's a balanced force because it's not falling over.
Right, it would fall over if it wasn't balanced, wouldn't it?
Yeah.
So we have gravity, which is pulling it down. So we know we have all these forces pushing and pulling, and how's it? That has to be equal. And if it's not equal, what would happen to that statue?
It would fall over and
It would
collapse.
fall down. Here's an interesting one. Did you guys know things don't stop moving because they run out of force? They stop moving because other forces stop them from moving. And that's what Ryder talked about earlier. Things like friction. Like if you kick that soccer ball, because you have the grass and the air and everything else, eventually that soccer ball, even if it doesn't hit a wall, is going to stop moving. Okay, you guys are going to do a dance. And here's your, everybody stand up. You're going to do some dancing. Yay! You have a song. And as you do the motions, I want you to think about words that you hear that are important. While you are dancing, think about words that are important to motion, since that's what we've been discussing this morning. So you are going to dance.
In this program,
How does it, you guys, I'm so sorry. It keeps doing it.
So go down. Go down.
It keeps doing that.
And then we're going to push and pull, push and pull, push and pull.
This is your motion dance. Get your hands
Make sure
moving.
that we jump side to side, we have our arms nice and close. Side
You're gonna move, move, move.
And last, watch and see. Watch and see. Watch and see. Now you're ready.
Nice job, Isabella. Good job, guys. What words? Oh, we got an encore. Yay.
This is weird.
Okay, no more encores. Yeah, we could see Mrs. Harrison. That was nice. Okay, what words did you hear that go with motion? All right, Madison, haven't heard from you today. You guys can have a seat. We heard push. What else, Gabe? What did I didn't hear you? Friction. Yes, good one. Gravity. Pull. All things we've been talking about. All right. So making things move. What speeds them up and what slows them down? I'm going to get the whole unit in one lesson. All right, so a force makes something move. Some forces make things move faster. Some make them move slower. We're going to check it out. So here's a boy. He's pulling a wagon. Where do you think we are going to apply the force to make that wagon move? At the head?
No.
Arm?
Yeah.
Or are we going to apply the force at the wagon? All right, let's see if you're right. That's right. There it goes. It made it work. No, that I don't think was a choice. All right, let's see. Now, if you're falling and sliding, and I could actually play it, I guess.
Some forces can't be seen. Gravity is the force that pulls objects down toward Earth's surface. When two objects rub together as they move, they create friction. Friction is a force that slows down moving objects.
All right, so you guys have all done this. You're Coloradans, so you know about friction. And I was talking, Gabe, when you were in the other room about you getting up this morning to go bike jumps and ride your bike, right, this morning on bike jumps and thinking about how fast do you want to go? How slow do you want to go? What's going to make you go faster? What's going to make you go slower? And we've been talking a little bit about angles and friction. And here's an example of that. I don't know, I'd want to go down that steep of a mountain or snow hill because I feel like I might go too fast. So mine wouldn't be such a steep angle. Okay, look at this one.
Speed is how quickly Speed is how quickly something moves. To measure speed, you measure both the distance traveled and the time it takes.
I'm gonna try. Let me do it.
Try the blue car.
It doesn't want to let me. Darn. Oh, it's gonna let me maybe. I just have to.
Which car is faster, the red car or the blue car?
Hmm.
Race each car around the track. How far does the car travel? How long does it take?
All right, raise your hand if you think it's gonna be the red car. Red is always faster, right?
Yeah.
What about blue? Oh. Okay, here we go.
I go with blue now.
Maybe it's a cautious driver. It's probably me in there. I'm really sorry. All right, 3 laps, 12 seconds. You guys can remember that, right? Let's see. Oh, yes. So let's do this. If it did 3 laps in 12 seconds, how long would it take for the red car to do 1 lap? 4 seconds each. Okay, let's do the, yay, thank you.
Yeah, I got the blue now. Yeah.
Oh boy, which one was faster? Blue. It only took how many seconds per lap? Madison, how many seconds per lap did it take? If it took 6 seconds for 3 laps, what would 1 lap have taken? How many 3s are in 6? 2. So it went, think if it was 2 for the blue and 4 for the red, it was half of it, right? Or double, the speed? Double the speed, we could say? Let's see. Come here. Is there next? Oh, we already did that.
You race
Okay.
both cars around the track.
All right, good job, you guys. So to find out which one is faster, we needed to know how far it would go and how fast. They went the same number of laps, just one took a little bit longer. So we're not going to look at that. I'm not going to look at that. Give me 1 minute. So now we've heard the word friction. And we've talked a little bit about it, but let's actually create some friction. Put your hands together. Rub them, rub them, rub them, rub them, rub them. And we are creating what?
Friction.
Friction happens when I'm going to ask real quick, guys. Everybody listening, a lot of side conversation here, and I can't think. Okay, guys? So, August, listen. So, when we rub objects together, we create friction. What else are we creating when we rub our hands together? Cooper? Our hands are moving, yeah, but what are we creating? Heat, energy, feel it. So guys, when I'm cold, I blow on my hands, I go, and then I go like this, and they feel better because I'm creating heat energy. Exactly, that's called friction. Here's a picture of a little girl on the slide, and it looks like she's having trouble getting down. Sometimes the material on whatever you're wearing against that slide can create friction and might slow you down. Or depending on the slide, it might be very slick and you might go flying down that slide, right? It's gonna do it.
If the stone can't go up or down, what about pushing or pulling it sideways? That's not so easy either. There is a force called friction. Friction occurs when one surface rubs against another. This makes sliding hard. When you put on the brakes on your bike, rubber tires on blacktop create a lot of friction and bring you to a stop. A rock and the ground create a lot of friction, making the rock hard to push or pull.
Okay, so friction is a big part of it. So we're gonna go ahead and do a little experiment. I want you to get out your science spiral. You're gonna do a little bit of predicting. Shoot, let me go back. And if you are at home, I'm gonna do my best to let you see this experiment. I want you in your science spiral to write these things down. You've got wood, cardboard, tile, and sandpaper. So I will write that down on mine too and then show you an example. You're gonna write the word wood, and then on another line, you're gonna write cardboard, and then you're gonna write tile, and then sandpaper. And I brought some other things too, but we're gonna just make sure we get through that. And then you can put a P for prediction if you want, and an A for actual. So you're kind of writing your own little double T chart. It's kind of the same as we did earlier with our forces. And then we're gonna actually do a little experiment. Okay. In the wood. I had so much fun, guys. I started finding all kinds of stuff. Cardboard, I got different kinds of tile. And then I couldn't find good sandpaper. And then we'll do a bonus. Okay, so what we're gonna do, and should I get out of this though, and I think it'll help? Yeah, so I'm gonna stop sharing my screen because we don't need it anymore. Now I'm gonna do the experiment. If you look in Mrs. Harrison's box, and I'm wondering if I tag you, Mrs. Harrison, can you tag you? You're it. I'm gonna try to pin Mrs. Harrison. I have to go to you. Huh? Okay, so now you'll be able to see the experiment better. So first, I want you to think about centimeters. Centimeters are small. They're not as big as inches. So we're going to do our measuring with centimeters, our predicting. So about the width of your thumb would be about a centimeter. So my question to you is, if I have this car and I put it on a piece of wood, how many centimeters high do I need to lift the wood? Can you see? Okay. How many centimeters high do I need to lift the wood before it'll start moving, rolling down? Write it in your spiral next to wood. What is your prediction? How many centimeters? How many centimeters?
And this is wood?
It's wood, yes. All right. I am going to start lifting. This ought to be interesting. There's 1 centimeter. 2. Oh! 2 centimeters. All right. Now let's do cardboard. Voices are off, my friends. All right. about the material and the difference between it. That wood was very smooth wood. How many centimeters do you think I'm gonna need to lift this for it to start moving? Write it down, make your prediction. This one is cardboard. Okay, I hear some thoughts that this could be a little harder. Centimeters. Because it's gonna happen pretty fast. All right, here we go. Oh, not backwards. I have to put it up a little bit. I practiced. Oh, I keep thinking like it wants to go. That's so funny. Okay.
Why is that car on the cardboard?
I think it was like 1, you guys. Hold on. It moved on 1 centimeter. Now watch. Did it go very far? Did it go very far, Josh?
No.
Watch what happens if I move it higher. Did that affect the motion? Yeah, quite a bit, didn't it? So when we talked about motion and all the things that affect it, did anyone say angle? The steepness, right, is going to change that? Okay. So the higher I went, the faster it goes. That's why I like my snow sledding hills to be not quite so high. After would it be right? Tile. Okay, so I'm going to do 2 different tiles. One is very smooth, and then I got travertine that's got some little bumps. I don't know, it's a little rougher. I was hoping they might be different. But let's go ahead. What do you think? We got the smooth tile. Write your prediction down. How many centimeters do you think I'm going to have to lift that to make it go? Okay, give me a thumbs up if you're saying 1. Give me a thumbs up if you think 2. 3? 3 or more? 3 or more? Okay, here we go.
No, it's either 2 or 1. No, yeah, 2 or 1. 1.
I think that was 1.5. Let's try again. 1.5. It's literally 1.5.
How do you
So
say
you-
1.5?
Right? Because when it started rolling, it was between the 1 and the 2 on the second sentence. So 1.5. All right, let's try this tile just for fun, because it is different. This one's travertine. So if you want to draw a half circle,
I'm not sure if I have to go that high.
1 half, and then at home, so it would be 1.5. 1.5. That's what it would look like.
There's another way you can do it.
Okay, we're just gonna do that for now so we can do it finish. All right. Do you think this is also 1.5? Give me a thumbs
I
up.
think it's 2.5.
2.5? All right, let's see if it's gonna be higher or lower. I think most of you are saying you think we're gonna have to go higher. Why do you think that, Cooper? Because it's rough. You think friction might play a force, be force here as we go? Let's see. 2.
Yeah!
It's 2 or centimeters. 2 centimeters. All right. Sandpaper. It's not super rough sandpaper, so make your prediction. If you think 1 centimeter, give me a thumbs up. 1.5, I heard over here. 2? More than 2. What do we know about sandpaper?
It's rough.
It's rough. Things that are rough can slow us down. What do they put on the roads when it's icy?
Snow tires?
salt to melt it, but also little gravel pieces, right? To slow us down so we don't slide. All right, here we go.
I'm going 3.5. Wait, you really started this on the wood.
Yeah, I can still watch.
I think 2.5.
That was 3.
I was gonna say
Why do you think 3? Abby, why do you think 3 centimeter? Why was that the highest so far?
because it's lighter than.
What do you know about the sandpaper? Why would it stay longer on the sandpaper?
Because it's rough.
Because it's rough. Okay. And that friction helps it, keeps it from moving so fast.
What's that? What is that? That's a thingy.
Okay. This one has 2 sides. You don't have, you can write this or just think about it. So this side is rough and this side is smooth. It's just foam, right? You can write it foam, F-O-A-M. Let's try the smooth side first. My husband found this, he's pretty excited. And this side is kind of rough. So let's do the smooth side of foam. Yep, listen to these. Yep, all right, here we go. The smooth side first. 1, 2, 3, 4 centimeters. Because even though this is the smooth side, it's still wet, Sawyer. Sawyer, even though this is the smoother side, it's still wet. Yeah, exactly. Okay, this is all I have time for. One more. This is the rough side. Make your prediction in your head. Here I go.
Wait, no, not 7. I'm going 5 through 6.
9. Wow, 9 centimeters. So this one caused the most friction. And friction is broken down. You just in your head, think of one thing you learned today, share it with your neighbor, and then Mrs. Harrison's class. It was so fun today. You guys may line up. My class. My class. I'm gonna see. Okay, I think I'm back. Maybe. Thank you. All right, guys. Great job today. We will see you at 12:45. I hope you enjoyed your science lesson.